My name is Tan, and today we'll be discussing the basic principles of the polar and rectangular forms of complex numbers. It's fairly simple, so without further ado, let's get started. There are two ways to locate a complex point, which is a point that's written in complex numbers. One way is rectangular and the other is polar. The rectangular form comes in the equation z equals n plus I, which stands for the point, equals a real number for the x portion, plus an imaginary number for the y portion. The polar form mirrors the x and y portion in cosine and sine, but it's different because it says z equals radius, the r is radius, times the cosine theta plus the radius times sine theta. It keeps, however, again, the imaginary number for the y portion. So the difference between rectangular and polar is that the rectangular form explicitly shows the coordinates of the point because it shows the x coordinate and it shows the y coordinate. So you can just plot easily the point on a graph using this form. Whereas polar tells us the radius, which is the distance between the point and the origin 0, 0. And it also tells us theta, the angle of the radius, that line, from the positive x-axis, which is basically where it's 0 degrees. Now, between these two, you can convert back and forth. If you're given the rectangular form, you can graph this and from there figure out the polar form. Or if you're given the polar form, you can take the radius and the angle of the radius to find the coordinates of the point, and from there you can write the rectangular form. Let's try the example going from rectangular to polar. So let's say we're given the point, the point, but the formula, the equation z equals -3 plus 4i. So if you look, it mirrors the equation, and we have a real number and imaginary number. So the graph of a complex number is very similar to the x and y coordinate, except the x-axis is still uses real numbers, so let's call that n. However, the y-axis is different because the y-axis uses imaginary numbers, as we can see in the equation. But otherwise, the process of plotting the point using the x and y coordinate is the same. Since it's -3, we go from the origin to the left on the x-axis 3 points, 1, 2, 3. This is where -3 is, which checks off the n. And for the imaginary number, we don't have to worry about the I because the y-axis is already imaginary, so we just have to worry about the 4. So it's positive, so we go up 4 distances, and that's where 4 is. So if we just plot this point, it's up 4 and over 3. So the point z lies right there. So now that we've graphed the complex number using rectangular form, now we can use this graph and write the complex number in polar form. So if we look at the equation for polar form again, we need to know what we're missing is the radius r and the angle theta. Now, as I said before, the radius of this point is the distance from the point z to the origin. So all you have to do is simply draw a line, and that's our line r, which is the radius. We need to find the magnitude of this line in order to plug it into the equation. Now, if you were to look closely, you would see that this is merely a triangle with the radius being the hypotenuse. Since it's a right triangle, we can use the Pythagorean theorem to find radius, because since we already have the magnitudes of the other two legs, we can use this to find the hypotenuse, which is r. We know that this distance is 3 because it's -3, and we know that the distance this way, upward, vertically, is 4 because the y value is 4. Now, if we were to do Pythagorean theorem, we can substitute in x and y to find r. So the x is, we can take out the negative symbol because we only need the magnitude, the distance. We don't care much about whether it's on the left side, like the negative y-axis, x-axis, or the positive. We just care about the value, the magnitude of the magnitude, the distance. So that's 3 for x squared plus 4 squared equals r squared, the radius. So if we were to solve this simple algebra, we get 25. And if we were to square root that, we find that the radius is 5. So now we know that this line has a magnitude of 5. So if we go back to this equation, we know that we still need the theta, the angle. And this theta that we're looking for is the angle from this line, which is the positive x-axis, the origin for a polar graph from here to this line. We need this theta. However, we can't find this theta unless we find the angle for this triangle and use that to subtract that from 180, which is this whole line. By doing that, we can find this theta, this angle. The reason why we're using this triangle, we're finding the angle for this and subtracting it from 180 to find this angle, is because we're given all the numbers we need in order to find this angle. So in order to find this angle, we just need to use tangent, because tangent of theta is the side opposite over the side adjacent, and the side opposite being the y, the side adjacent being the x value. And we are given initially, and we have drawn out those two values. We still definitely could use, because we're technically looking for cosine theta and sine theta separately, we could find the sine, sine theta, because we now know the radius. For to explain, sine theta would be the opposite side y, 4 over the radius 5. So we could set the equation as sine theta equals 4 over 5, and from there find theta. But let's say, for example, we didn't find the radius first and we were looking for the angle first. Then we would need to use something that doesn't require the radius, which would be the other two sides, the x and y values. So if we are looking for tangent, because tangent equals sine theta over cosine theta, which equals y over x And like I just said, we have those two exact values, the x value and the y value. All we would need to do was plug that in. So since we're looking for theta, we need to do the inverse tangent and plug in y and x, which is 4. And as for the x value, since it's negative, you can plug in -3, but this would give you a negative degree, and that line would go here. From here, you can just add 180 because this horizontal line has the value 180. So all you would need to do was add pi or 180 in order to get this value, which we're looking for. Or another way you can do that is just plug in simply 3, because like I said before, we're more concerned about the magnitude rather than where it is, because after we get this value, the theta that we're going to use, we can adjust that number accordingly to where it lies, which quadrant it's in. So I'll show you this method. So if we're to plug in 3, the theta we get would be so inverse tangent 4 divided by 3, and we get 53.1, rounded 53 degrees. And it's clear that this would not be 53 degrees because it passes 90 degrees. So this 53 applies to this angle. Now, how can we get this angle after we know this angle? And that applies the same for this idea, because a horizontal line is 180 degrees. So in this case, if we were to plug in -3, we would get -53 degrees. And from there, we can add 180 degrees to get this angle. However, we have a positive 53 because we used +3 instead, and we got this angle. In order to find this angle, all we need to do was subtract 53, this angle, from 180, and we would get this angle. So we were going to do that. We get 126.9, rounded 127 degrees. And that's the value for this angle right here. Like I said before, 53 degrees. And let's plug this into this equation. So we know that the radius equals 5, and theta, the theta we're looking for, is 127 rounded degrees. However, we can't use this in the formula. We have to convert this into radians. So all we would need to do was take the degree that we got and convert it, times pi divided by 180. 2.2 is our value for radians, so equals 2.2 radians. And this is the value we'll use to plug in. So if we were to plug it in, we would get don't forget the imaginary number. And in order to separate the radius value from the degree, so we can clearly see what the polar formula gives us, we can factor out the radius, and that leaves us with cosine 2.2 plus sine 2.2 I.